Hi everyone. Thanks again for joining this webinar. We're actually very excited about it. It's the first ever webinar we are organizing here at Prior Labs. So I think it's the best moment to actually get a walk through TabPFN, seeing it in action. And we're also super lucky to have Frank Hutter, the co-founder and CEO of Prior Labs, and also Carl McBride, which is a Kaggle grandmaster and who actually played around with TabPFN and will show you some of his results. So I leave the floor to them. Enjoy.
All right. Hi, everyone. Yeah, it's my great pleasure to have you here for this first webinar, and super happy to have Carl here, our first Kaggle Grandmaster. And yeah, really looking forward to seeing TabPFN in action from him later on. First, I would like to give you a bit of an overview of what TabPFN can do, what it like how it works, and then pass over to Carl. So the TLDR is that after years of false promises, where deep learning claimed to work really well on tabular data, now it actually does. So here's a plot of all kinds of different methods, random forest, all kinds of gradient boosting methods, and then 5 different tabular foundation models that were all published in the last year. This is on up to 10,000 data points and 500 features on Tab Arena. Yeah, the community is scaling quickly to larger data sets as well. But for these small data sets, very clearly, tabular foundation models have now actually taken over. All right. The agenda is, well, I will give you an intro to tabular AI and TabPFN, and then we'll see the Kaggle live demo from Carl, and then Q&A. All right, let's get right into it. So in case, yeah, just to make sure that we're all talking about the same thing, what is tabular prediction? So it's really this decade-old problem formulation that many of you saw in Machine Learning 101, where you have some training data, X-train, so features. You have a target that you want to predict, and then you have test data for which you have the features, and then you have you want to predict the target for these test values, and you want to do this probabilistically. For example, say here the response in this case, it's a positive lead in health insurance lead prediction would be 24% here, 91%. So you would, of course, call this person first in order to sell them an insurance in this particular case. This is just one out of thousands of different problems. A few further ones are like, will this customer churn? Which product will this customer buy? For this particular patient, will this treatment work? Or which treatment should I propose? Etc., etc. All right, so that's tabular prediction. Tabular data is everywhere. It's in all kinds of different databases and tables in the enterprise. And while foundation models have transformed text and images, there's this gaping hole for tabular foundation models where all of our valuable data sits. So there's all these startups for text, ChatGPTs, and so on, and images like Black Forest Labs, for example, also here in beautiful Freiburg, where I'm sitting. But for tables, time series, and databases, yeah, there is this big hole, and this is being tackled now. All right. So foundation models, they really change the way that people are working in the context of tabular data. What you would used to do is say there is a claims data set. You have to collect the data, you train a model, and then you predict for this particular claim is this fraudulent, for example, 15%. But this training, this is actually a data science project in itself, which if you're really good, you Carl, then it might take hours. But typically this takes weeks, months. You need to do missing value imputation, feature selection, model selection, training, hyperparameter tuning, all kinds of stuff in order to actually get a strong model. And this was just one application. And then you have another question. What's the lifetime value of this customer? You run through this again. And which product does this customer want to buy next? And you run through it again and again and again. Whereas with foundation models, this can be a lengthy task-specific model selection and training and leads to these individual siloed models that don't actually talk to each other. So there is no positive transfer between them. Whereas in foundation models, the task is different. You actually take all kinds of different data sets, build a model across data sets. You train this on, if you have the millions of different data sets, and then you can actually use this off the shelf without retraining. Like you don't retrain your ChatGPT, you just use it off the shelf and actually just do forward passes with it. And just like that, with our foundation model TabPFN, we'll only do forward passes in production. And you can also actually, if you have related data sets from a particular application that are all somewhat similar, then you can actually learn across them. You can fine-tune your model to a particular application and build a foundation model that is fine-tuned to your particular application at hand. All right. And our community is on its way to actually get there. We're revolutionizing tabular data. One milestone here was the TabPFN v2 publication in Nature in this January that showed 96% win rate against previous methods such as CatBoost. And importantly, you only need less data in order to get the same accuracy. So only 50% of the data needed than with CatBoost to get to the same accuracy. And if you have, I don't know, you run for example, a case study in like a patient cohort to test a new drug, and you can get away with 5,000 patients rather than 10,000 patients, then you just save half the money on this particular study, and this might be millions of dollars. Also, we have open sources, and there's almost 2 million downloads. We have 4,500 stars on GitHub, and the open source is used in a lot of different companies. All right, on a high level, how does this work? So this is sort of the one slide on how does it work. So if you care about that, pay attention for one slide. We have basically the big difference to previous deep learning methods is the input to the neural network is now not a single row, but it is the entire data set. So it is the X-train, Y-train, X-test, and then a question mark. So we have a data set where we have the true Y-test. We take that out. We push this entire data set in a set-valued fashion, set-valued input into the TabPFN. TabPFN makes predictions here, these multimodal predictions for the Y-test. And then we just take the real Y-test and look how likely is it actually under the prediction. Then we backprop that, update the parameters theta of our TabPFN, and then iterate. So for one data set, we only have one backprop stage rather than having a backprop stage for every data point. And then we sample a new data set and do this all again and again and again and again, and actually hundreds of millions of times. So we need hundreds of millions of data sets. There aren't hundreds of millions of data sets of real data sets on the web. In contrast to text and images, people don't actually put their tabular data sets on the internet. But here, actually, we came up with a way to synthetically generate these data sets. And that is a main contribution of TabPFN, to actually generate synthetic data sets that look like real data sets, that have all kinds of causal relationships in there. And mathematically, what we do is we actually approximate the Bayesian posterior over all possible structural causal models that could explain the data. So then after this pre-training, we have this TabPFN, and then this is the first time that a real data set comes in. And this is a data set you want to predict in, just like you would predict with XGBoost, etc. You have your X-train, Y-train, X-test. You truly don't know the Y-test. You feed this to the TabPFN and makes predictions for the Y-test in a forward pass. All right. So how well does this do? Well, qualitatively, it actually yields very nice, smooth, and well-calibrated predictions. You see here, there's the scikit-learn toy data, this half-moon data, for example. And you see that away from the data, TabPFN is very uncertain. White is maximally uncertain here. Deep blue is maximally certain that it's a blue class. And you see, for example, the tree-based methods are very axis aligned in their predictions and sometimes have sort of weird confidences, whereas TabPFN away from the data is very unsure. And that is how it was trained, because the training loss was cross-entropy, and cross-entropy really penalizes being wrong and sure. So if you might be wrong, then you want to at least be unsure, and that's what's in the loss, and then it's also well calibrated when it comes out after optimizing for that loss. All right. It's super simple. As I mentioned before, it's just a forward pass. Up here, this is sort of the pipeline of AutoScaLearn, which I love, which we developed in 2015, which is this AutoML tool around scikit-learn that picks the different data preprocessor, feature preprocessor, classifier, etc., runs Bayesian optimization, does meta learning on top, builds an ensemble at the end. Super cool, super complex, but a little bit too complex for practical data scientists. They actually want to have a quick method and they don't want to wait over the weekend while the system is running. In TabPFN, you put in the data, it is a forward pass, you get on with life and iterate. And you can do all the fantastic things that data scientists are great at, like feature engineering and so on. And you don't have to wait like 48 hours until you can iterate, but rather like a few minutes. All right, quantitatively also works really well. So for classification first, here we have a linear regression, MLPs, SVMs, random forests, and then LightGBM, CatBoost, and XGBoost. We have them in the default that takes typically some seconds, and the tuned version, tuned for 4 hours. And we see that TabPFN actually within something like 5 seconds is actually much better than 4 hours of tuning of the different boosting methods. And we also see that in this plot here, after 5 seconds, it's already much better than the others after 4 hours. This is a result that holds on average across data sets. It doesn't hold for every single data set. For example, here we do have a data set, 1 of 29, where CatBoost is a bit better than TabPFN, but for the other 28, TabPFN is better. This is for the default, and this is for the tuned version, where you see even sometimes greater differences. For regression, the story is quite similar. The differences are not quite as big because we didn't actually focus on regression as much in V2. We're putting more love there right now. But you still see, yeah, in 5 seconds better than the other methods in 4 hours. And a few more data sets where CatBoost actually is better than TabPFN here. Then we also compared this to the best AutoML methods and also integrated things from AutoML. I kind of started the AutoML community, and of course I would love to still keep using all the best stuff from AutoML, and here we are. AutoGluon is based on a lot of really cool ensemble methods, this post-hoc ensembling in particular. And so here we see like 5 seconds of TabPFN is about as good as 4 hours of AutoGluon. AutoGluon combines all the previous traditional machine learning methods. This is AutoGluon. This is a plot from the papers in January. So all the methods that were there before January assembled in the best way with post-hoc assembling in AutoGluon in 4 hours. Gave you the same performance as TabPFN in 5 seconds. But then you can tune TabPFN further and also actually assemble different TabPFNs with slightly different architectures, and that gives you a yet greater boost. And for regression, this is actually important, where just the default zero shot, it's not as good as AutoGluon after 4 hours. But if you tune it and then you put the PHE on top, then you still get a 70-30 win ratio here. All right. It is a foundation model. So as a foundation model, you have foundation model capabilities such as fine tuning. You all know that you can fine tune LLMs like ChatGPT, or you download a Llama and you can fine tune it locally to your type of text. And just like that, you can download TabPFN and fine tune it to your data sets. So here's a plot again from the paper that is on a sinusoidal curve. So in yellow here, we have the true sinusoidal curve. The orange are data points that TabPFN sees. And the prediction is okay. It just doesn't know that this is a sinusoidal, so it's not great. But then if you fine tune on a couple of sinusoidals, it gets dramatically better. And we also here fine-tuned on some real data sets that are not synthetic, and it actually does get yet better. So here sort of closes half of the gap between TabPFN's performance and perfect with respect to this metric. Further foundation model capabilities are density estimation, data generation, and also you can take the embeddings of the penultimate layer of TabPFN. And for example, if you run PCA on those, that's much better than running PCA on the original data. Interpretability is actually really nice. So a plot from before again, we have smooth predictions and reliable uncertainty estimates. And that leads to post-hoc interpretability methods actually being much more interpretable than before. So here we have SHAP for TabPFN and for CutBoost. And CutBoost has these really sort of axis-aligned and not very smooth predictions. And that leads to pretty noisy SHAP plots, whereas here you clearly see this blue class is increasing sharper than the red class, and there's this gap, and at some point they cross. All right. You can also do cool new stuff where we're doing a lot of research on these prior fitted networks. And so you can do things like a proper what-if analysis. So what standard machine learning models do is for a particular row, predict, okay, what will be the outcome? But they can't say, well, if I take this row and I change this feature, what would that do? That is actually something where standard machine learning models, be it XGBoost or also TabPFN or anything, is just systematically biased. But you need causal machine learning methods in order to do these types of interventional queries. And we just have a paper that's a spotlight at NeurIPS this year with Bernard Schirkoff as last author, who is like one of the really strong researchers in the world on causal ML. This method is called DoPFN in the TabPFN framework, and that actually allows you to ask these questions. What would the response be for this particular row if I change this value to a different value? All right. You can do time series forecasting with TabPFN. So there you have a time series. This is your historical data, and you want to predict for the future. And you can featureize this data just by actually getting the running index, the year, the day of the week, etc. And you can do that for the past, but also for the future. And then you want to predict how high is this time series, in this case, univariate in the future. And that's just the, well, X train, Y train, X test, and you predict Y test. So just feed it into TabPFN. And very surprisingly, this simple method in January this year, when we tried this on Giftival, which is this leading benchmark for time series forecasting, it was actually #1 on this benchmark, above Amazon Chronos and Google's TimesFM, which are far bigger models. And these models are also actually trained on real time series data. And TabPFN was just the model from the Nature paper that had never seen a time series in its life. It's never seen any real data. And nevertheless, it actually did better on real data from time series forecasting than these other models. Of course, this just went to show that there is so much room left for time series, and you can do much better by pre-training and fine-tuning on time series. And of course, we're doing that right now as well. All right. With Prior Labs, we have this TabPFN, we have TabPFN time series, we have TabPFN Plus that integrates text. We're building TabPFN v3 right now. There's all kinds of things we can do with tabular data, and we are completely horizontal across different industries and applications. And well, we're going to look into one of them today. Here's sort of an overview of different types of verticals we've looked at applications from, but this is really just, the tip of the iceberg. There's tabular data literally in thousands of different applications. And with that, here's the takeaways. So tabular foundation models are really the new state of the art for small tabular ML. They're faster than previous methods, better peak performance, and work well with less data. You can do fine-tuning, can do other foundation model capabilities, and they allow you cool new stuff like counterfactual reasoning, interventional reasoning, etc. We have open source, and with that, next up would be the Kaggle live demo, and in the end, we'll take questions for both Carl and me. So without further ado, over to Carl.
Right, thank you very much. Wonderful. Okay, what we're going to do is I'm going to share my screen and we're going to do a walkthrough of let me just make sure I get this right. Are we seeing the competitions page?
Yes.
Yep.
That's right.
Excellent. Right, what we're going to do is we're going to take a look at the Kaggle competitions page, and let's have a look at what we've got. We have a road accident. This is October, September. Let's have a look at this one from August. Okay, binary classification with a bank data set. So let's. We're limited to. We can't do as much data as synthetically generated on a Kaggle competition. So what we'll do is let's go to the data section and find the original data set. Here we go. And let's work on this for a little bit and do a very simple comparison between CatBoost and TabPFN. So let's start up a new notebook here. Here we go. Right, let's get rid of this boilerplate. So, gone. And let me just bring in a little starter boilerplate that I like to work with. This notebook will be available to everybody after the meeting. So, let's start this up. Takes a while for the session to start on Kaggle. In the meantime, let's get ready. There we go. Right, let's have a look. Right, that's not very nice at the moment. But what we can see, okay, this is a semicolon delimited data set, so let's reread it in. That's much nicer. Yeah. Okay, so we have our target column here, etc., etc. All right, that's looking good. Right. Okay. Next step. Well, let's just see what the target's got. Let me just bring in that and run that. Okay, so a binary classification. No, 40,000. Yes, 5,000. As percentage was 88% negative class, 11%, 12% majority class. Okay, that's okay. That's fine. Right. Let's recode that to work with the metrics that we're going to use. So that's looking good. I don't think we actually have to do this, but like I said, when it comes to the metrics, it's nice for them to be integer values. Right, so that's good. That's good. Let's have a look. We're going to have a look at if there are any missing values, but it must be said that both CatBoost and TabPFN are resilient to missing values, so it's not a concern at all, but it's always nice to check. So let's see what we've got. And we seem to have no missing values at all. So we're looking at an is now, sum of a sum, and there are no missing values in any of this data set. But even if there were, that's not a major concern for neither CatBoost nor for TabPFN. What sort of data do we have? Let's have a look. Yeah. Okay, that's good. Yeah. Excellent. Fantastic. Right. Let's have a look at what the counts are on these features. Make sure there's no categorical that has thousands of values and really should be treated in a special way if it were so. So let's look. We're going to call them cat features. Any of these object columns, let's call them, stick them in the list and call them cat features and have a look. So we got jobs, blue collar, management technician, unknown. So there are some missing values that have been pre-labeled for us. That's nice. Married, single, divorced. No default, no yes. Housing. Okay. So we got some temporal data here, but we're not going to do anything with that at the moment. Let's just leave everything as it stands. Yeah. Okay. Well, we're working with an imbalanced data set, but let's give the majority class a fair shake of the lamb's tail at the same time. So let's undersample this so that we're going to play just as many data points for the minority as the majority class. So let me call in a little helper to get to do that. Let's bring in a little function. Right. So we're going to undersample this data set, which means keep all of the majority class and take a random sample of the corresponding length of the minority class set. So let's do that. Okay, so let's have a look at the Y counts, see how that turned out. Let's cut and paste this from up here. That'll do us nicely. Let's just go down. What happened here? Oh, I see. Y. There we go. So we got 5,289 examples of the minority class and 5,289 in the majority class. We do not need to do this. This is we're doing this to prepare the terrain for holding out some data to look at the calibration later. But there's no problem with working with imbalanced data with either of these estimators. That's good. So let's extract from that 2,000 points. Let's extract 2,000 points of data for later use in a calibration set. There we go. Okay. Right, let's call in a couple more routines. We're going to do cross-validation. So let me pull that in there. So look. We're going to do cross-validation. So here's a cross-validation, stratified cross-validation routine, 5-fold. And what we're going to do is we're going to, each of the 5 folds, the 20% fold, we're going to keep each of those outputs and then stitch them all together. So we got predictions, out-of-fold predictions for all of the rows of our training data in a new column. Okay, so let's we'll do that, and let's also create load in a routine or a routine to return some metrics. All of this will be in a notebook. They'll be available to everybody after this session. So we have here, we're going to print out the baseline scores. It's always really important to know how much we're improving with respect to a baseline. We look at the accuracy score, the Matthews correlation coefficient, the AUC ROC, not my favorite metric, it must be said, but we're going to look at the probabilistic metrics, log loss, and Bria score as well, which and the confusion matrix. Okay, so this routine will take care of all of those for us at the same time. So let's start with cat boost. So let's look at cat boost. So scrolling, look. Kaggle notebooks already come with cat boost already available. Cat boost 1.2.8. And let's run it. So we're going to call in the cat boost classifier. We're going to mute any of the output. Where the object, this cat boost does need this. It needs the object. Here we go, scrolling up. These objects to be labeled as the cat features. TabPFN can deal with this without specifying that the object columns are cat features. It does it itself, but cat boost does like to be told. And just run those two routines. So let's right, yes, let's run those. Run that and run that. So we're performing in the background the 5-fold cross-validation, calling a routine here, providing all of the X and all of the Y data, and we're going to save both the dichotomized predictions and the probabilistic predictions here. Then send those to the routine to calculate the classification metrics. And I see. That's good. Missed out one of the routines. Right, here we go. Let's add that in there as well. Code. Okay, let's rerun just that here, so not waste time. Okay, there we go. As we're using balanced data, the baseline accuracy score is 0.5, the ROC AUC is 0.5, the matrix correlation is 0, the baseline log loss will be the natural logarithm of 2, and the Beer score is 0.25, 0.5 squared. So we see an accuracy score from cat boost here, 0.86. The baseline corrected accuracy scores, that's taking the baseline from the accuracy score to see how much uplift our routine gave us. 0.36 above baseline. Matrix correlation 0.73, AUC ROC 0.93. We have a confusion matrix, the log loss, and the Beer score. So let's repeat this routine, what we've done here, for TabPFN. So you'll see it's just as simple to run TabPFN as it is to run cat boost. Although I'm just realizing that I didn't switch on the GPU. So let me just do that now. I forgot to do that. We do need to use the GPUs to run TabPFN. So this is going to reboot the notebook. So in the meantime, let me just drop in the code that we need to run TabPFN. So first we will install TabPFN because it doesn't come at the moment with the Kaggle environment. So here we go. And take a look at the version. And the same same setup as we used for cat boost. Specify the classifier and perform cross-validation. Okay, let's go to the top and let's run all this through. Now using the GPU. So we're firing up this session again. I forgot to turn on the accelerator here in the sessions options on the right-hand side. Here we're using the T4s. They're not particularly new GPUs, so they're not blazingly fast, but nevertheless, they get the job done. So still waiting for the session. Here we go. Right, now we're in business. Right, so that's running. Here we go. Okay, there we go. But that wasn't really needed. That's duplicated. Right. So now we're installing TabPFN. And we see here, it's just as easy to use as Cat Boost or the other famous estimators. We're simply calling TabPFN classifier. Notice we're not using any options whatsoever. No flags are passed at all. Just using the vanilla version for today. In later sessions, we can go into more depth on other options that are available, and perhaps regression as well. But here we are, just TabPFN classifier, as simple as that. It's just pulled across the weights files from Hugging Face, I believe. So that's 29 megs there. As mentioned, these GPU T4s are not amazingly modern, so not particularly fast as far as GPUs are concerned. There we go. So what we're seeing here, the confusion matrix, we're seeing log loss 0.3102 compared to 0.3261, and the beer score 0.0938 compared to 0.994. So we are seeing an improvement for TabPFN classifier with respect to the baseline CapBoost classifier. In terms of dichotomized metrics, accuracy score for CapBoost was 0.865, and we're seeing here 0.8743. So 8786. So it's almost a 1% improvement in accuracy score there. There we go. Right, let's have a look at that. Let's plot the rock curves out. So let's make use of the scikit-learn rock curve display and compare the rock curves for the two. We can see here CapBoost is in blue and TabPFN is in orange. So we can see, at least in this region, the TabPFN, I don't know by not too much, but we can see it's superior to the CapBoost curve in this region. Let's take a look at a histogram of the probabilities. This is the main reason why we balanced the data set. So we can see a good spectrum. We get a good spectrum of both the negative and the positive classes. Now this is quite interesting. In this histogram here, we're going from probability 0 to probability 1. We're plotting the probabilistic predictions, and we're seeing here. Well, let's zoom in on these regions. Let's zoom in on these regions. Let's look at the lower region. This is very interesting. See here, this is CapBoost is in blue, and we're seeing TabPFN is far more confident about the negative class than CapBoost. In these very, very small values, it's really quite confident about what it's seeing. Let's try and look at the upper region as well. What we got here, we're going between, what's that, about 0.9. So let's go from here, 0.9, 0.9 to 1. Let's have a look at that. Okay, don't see it quite, so let's reduce the number of bins a bit. No, we're not seeing it quite as clearly as, maybe let's drop that to 8. Well, what we're seeing here is this is TabPFN and this is CapBoost. On the other hand, CapBoost seems to be more confident about the positive class. Well, then let's have a look at how well calibrated both of these are. So we're going to do a full fit now. We're going to fit the model to all of the XY data and make use of those two. If I scroll back up, make use of those 2,000. That test size of 2,000 I set aside earlier. Let's use that to compare our calibration. So let's run that, and let's do the same for TabPFN. So we're fitting the full to all of the training data now, rather than cross-validation as earlier. And that's finished. Let's do TabPFN at the same time. Whilst it's running, let's look at the so these confusion matrices we got. This is CapBoost 3570719 35. So these are quite similar. Okay, the true negative and the false positive are quite similar. But we're seeing here 438, 350. There's a significant improvement in TabPFN respect to the false negatives. A lot fewer false negatives. 3851, 3936. We're looking at 80 more true positives. So here we're seeing less false negatives and more true positives are being returned by TabPFN. This is good. Right, those are finished. So let's to finish up. Let's take a look at the calibration displays. Let's have a look. Let me just pull across the Scikit calibration display for us. 5 bins. And we can see that both of them are fairly respectable. They're both fairly close to the perfectly calibrated diagonal line here. So not too bad at all. Not too bad at all. Right. Well, I think with that, we'll return to the Q&A session. Like as mentioned, this notebook will be available to everybody briefly. Okay.
All right, thank you so much, Carl. And I guess we're up for the last part, which will be the Q&A. So I see that some of you already did put the questions in the chat. Frank
Yeah, there were
already
a lot of great
started.
questions. I tried to answer a bunch, but have definitely not answered all. So
Yeah,
yeah,
I think it'd be
let's
great
have them.
to start looking at some of them again. I guess the question that is happening that we had quite a few times, but can you recommend sampling strategies for working with bigger data sets in TabPFN, or overall, how do we actually use TabPFN for larger data sets? I think if you can.
Yeah, so it's definitely that is a tricky question because there's a gazillion methods you could use, and we're currently looking into kind of all of them. We're of course building a model that's a better base model and can handle more data in itself. But then there is retrieval and fine-tuning. Fine-tuning, we have a fine-tuning method where you can, for example, have like 1 million data points and then fine-tune on batches of, say, 10,000 data points at once. There is a method that we actually had already in the Nature paper, sort of mentioned in one sentence there because the space constraint was pretty heavy, that builds trees, like decision trees or regression trees, and has a TabPFN in all of the leaves. So the leaves, the trees would be pretty shallow. So you just build out a tree as usual, and if you have less than 10,000 data points or less than some factor, 5,000, 2,000, whatever hyperparameter, then you don't continue building that tree, but you just put a TabPFN. That actually scaled much better than what some people did, is just to subsample the data. Like we had a post on LinkedIn and Twitter at some point with 50,000 data points, looking at you can subsample the data and just put 10,000 at a time. But that's, of course, not very good, right? I showed this result that I'm actually super happy about, that with half the data, we're as good as CutBoost with the full data. But 10,000 is not half the data of 50,000, it's actually less. So in some cases, 10,000 was still better than 50,000 in CutBoost, but in some cases, it was also worse. But then if you have this decision tree and only have the leaves with 10,000, actually have a TabPF, and then it would be much better. And you can also, of course, expand this to random forest and so on. And yeah, so that is a further way of scaling up. And yeah, we're looking at a lot of different possibilities right now. But the tree-based TabPFN, that is actually implemented in the auto TabPFN, which is a part of our TabPFN extension package. And the auto TabPFN is actually basically the TabPFN PHE in the Nature paper, and what I also had on the slides here. Right.
All right. Another interesting question was Are these good performances only seen on strictly tabular data, or do we see them for other kinds of data converted to tabular as well?
Yeah, so that I did answer in the chat already, but we have the TabPFN Plus that actually takes textual features and throws them through a language model, takes embeddings, put that into TabPFN, and that was actually quite a bit better than other methods that are that put a lot of effort into training for multimodal tabular text data, such as CART or also autoglue and multimodal. So yeah, that it was sort of surprising to us. Just TabPFN never saw any text embeddings, and it could just still deal with text embeddings really nicely, which sort of is nice. It sort of goes to show that both text embeddings work well and TabPFN work well.
Another question you already replied, but I think it's great to say it out loud again, which is a more general question. If there is time afterwards, can you explain how the in-context learning is implemented in TabPFN from the architecture perspective, and how does it allow learning of new tasks?
Yeah, so I mean, from an architectural perspective, you feed in the entire data set, right? So the data set becomes part of the prompt, and then it's trained to take that prompt, X train, Y train, X test, and output Y test. And so the forward pass that actually implements an algorithm, and that algorithm is now it's sort of the natural continuation of AutoML. Like if you have, for example, yeah, to go from like standard features for computer vision like SIFT and Hawk and so on to deep learning, actually you now have automatically learned features. And TabPFN is actually an automatically learned algorithm, whereas XGBoost is actually a hand-coded algorithm. TabPFN is a learned algorithm, learned across millions of different data sets to take this data and in a forward pass actually output Y test, such that Y test actually shows good cross-entropy losses. And it it is very complex to explain how this is actually implemented, like what every neuron does in the TabPFN. But the way that TabPFN can do it, we have attention that is going across all the data points, and then we have attention across all the features, and then we have that in many different layers. So every data point, every entry of this cell can communicate with every other entry of the cell. And of course, neural networks are yeah, like due to the universal function approximation theorem, can sort of compute anything, and also a couple of layers can compute anything. So yeah, and we have pretty complex functions in there, then it can just learn all the complex functions that are complex enough to tackle the data, but not too complex to overfit. So we do show and we really constrain it not to overfit by training it on data sets that rather have simple explanations rather than complex explanations, so that it doesn't overfit.
Another question is, would the forecasting work if the timestamps of the measurements are not fixed intervals? And then if there's a minimum of data entries expected or required to get the most.
Yeah,
and
yeah.
I mean, also, like if the variables change over time. I mean, this question is coming from someone who's, I guess, from the clinical trial field.
Yeah, so if you in particular the TabPFN extension is just really simple. It's just every data point that you have, you just give it a timestamp. And the featureization then happens with all the data that you have, and it's not autoregressive. It doesn't just predict the next timestamp and conditional on that the next one, but it can just you learn up to here, then you want to predict 17 days in the future. You do that in one forward pass, not in like 100 forward passes for each of the individual timestamps in between. Yeah, does that answer the question fully? Want to pass forecast a patient variable in the future? Yep, yep.
Okay, another question that we had was navigate the ecosystem of the TabPFN extensions, which I think is a great question. So the time series TabPFN apparently overlapped with TabPFN data synthesizer, for example.
So does a TabPFN overlap with a synthesizer?
The question is like, can I use time series TabPFN overlap with TabPFN data synthesizer? So I guess how to navigate the whole.
Oh, I see. I don't know. I actually don't know. I don't see a reason why not. The code might not play well together. I'm not sure, but I mean the basically what we do for data for synthesis of data sets is you just basically in order to like do a fill-in of like if you have like 100 rows, say, and then for the 101st row, you want, and say you have like x1 and x2 already, and then you want x3. You actually drop everything. You take x1, x2 as the training variables and x3 as a target, and just do a forward pass of that and just fill in x3. And then you do the same thing for x4 and same for x5 and so on. And so you can just iteratively with one forward pass fill in one value at a time. And just like that, you could also roll out the time series. I don't see why it wouldn't work. Not sure the code works nicely together because TabPFN extensions are individual extensions, and we sort of consciously didn't make it one big package in order not to have a sort of the combinatorial explosion of different dependencies. But and when you improve one method, have to make sure that it actually works with every other method. But like each method by itself, we've checked. More we haven't checked.
I guess we still have time for a couple more questions if we go.
Is there anything for Carl, actually? If you read from the beginning, they're probably all for me, but in the end, there's no for Carl.
I mean, we do have, thank you very much for the great walkthrough to Carl, great practical walkthrough, so more congratulations. Then questions, or did I miss one?
Okay.
If someone wants to write right now. In the meantime, there is a question on what are you observing regarding labeled data needed for ICL in terms of quantity and quality?
I mean, so we have not trained a model that tries to work well like with like 5 data points or so, that because it's, you know, that might just overfit the data very quickly. But like 50 data points we have looked at, for example, but you know, if it's 50 data points that are super noisy, then it will not work well. I'm hard pushed to give a clear answer. It's just we have observed that half the data of like your traditional methods have sufficed to give good performance, but you know, if you have more data, you're gonna get better performance. So tricky.
And maybe the last question, is there a smaller quantized version of TabPFN to run on our machines? I see this question got upvotes.
There is not as of yet, but that is actually good to put on the roadmap. Maybe we should do that.
We do have a question for Carl, which is, in your experience, do you have an intuition on the kind of data set on which TabPFN would outperform CatBoost and vice versa?
No, because I don't leave it to intuition. I run the 2 estimators and see how they come out. It's not. It's all down to running the numbers, and see what happens. Yeah, it's hard to have an intuition as to what numbers are going to come out until you've calculated them. So, so no.
So maybe like we were asked by the reviewers for adversarial data sets, and if we generated a data set from decision trees, CatBoost was better on them than TabPFN. TabPFN was particularly good at smooth curves and boosting very much at these axis aligned data sets, but which real world data set will be axis aligned? Carl probably knows this better than me. I don't. But another question for Carl here. An example where you would not recommend to use TabPFN.
If you don't have a GPU, because if you don't have a GPU, then I think the limit is probably 1,000 rows of data, if I'm not mistaken. And then, so if you do have a very small data set, it will run on CPU. But if a large data set and no GPU, then for practical reasons. But the answer is to apart from the pragmatic reason for estimator reasons, the same answer as before. I wouldn't recommend using or not using a priori. You have to run the numbers. You can't look at a data set and say what's going to happen. That's the way things are. Yeah.
And in terms of GPUs, like literally, we used 6-year-old gaming cards for the Nature paper, RTX 2080s, and that was fine. And that gives you like 50-fold speed ups over CPU. So any type of GPU is great. And we also have the API version. So if you have some data that you are happy to share, just throw it on the API and we pay the compute. So you can just run it there. Do not put anything there that's sensitive. We will at some point release a private API, but right now, whatever you upload to the API, yeah, we have to deal with. So don't put personally identifiable information there because we'll just have to filter it.
All right. I mean, I think we need to keep the schedule tight. I see some more questions popping up, but please, we will do a follow-up of this session. Feel free to share all your questions by emails to Frank, to Carl, or myself. Thanks again for joining. It was a pleasure to have you, Frank, Carl, and all the attendants join this session. And we will have some more of this type of webinar, maybe going further into detail for specific industries, specific use cases. So, I mean, I see people clapping. If you're happy with this format, we will push this further. And yeah, thank you, everyone.
Yeah, and thanks so much. Really great questions. Great to see the audience so engaged. Thank you.